So next special semiconductor device that is nothing but the tunnel diode. So it is a PN junction diode with heavily doped P and N regions. So normal PN junction diode, they won't be heavily doped, but these are some special kind of diodes where the P and N regions are heavily doped. They are designed specially for negative resistance region, and such diodes are referred as tunnel diode. So what is that negative resistance region in the sense? So whenever there is an increase in the voltage value is observed, the current is going to decrease, or vice versa. Or if there is an increase in the voltage, if you increase in the current, then the voltage will decrease. So that is nothing but a negative resistance region, or you can say that doesn't obey the Ohm's law. This tunnel diode was first introduced by the Leo Isaki, hence it is named after him as Isaki diode. Unlike as the P and N regions are heavily doped, unlike normal diode, the depletion region will be very thin. How much? It is approximately 1/100th time thin that of normal PN junction diode. And here we won't be using a normal semiconductor material to manufacture these. We will be using some special compound, that is gallium arsenide, so which is used to manufacture or which is used to construct this tunnel diode. So here this diode is going to work on the principle of tunneling. We will see what exactly the tunneling means. So here you can see the construction. So since the P and N regions are heavily doped, you will be getting a very thin depletion region here, and it is the symbolic representation of the tunnel diode. We will see the working here. So in tunnel diode, P and regions are heavily doped. Due to this, the width of the depletion region is reduced considerably, and the width of the depletion region of the tunnel diode is very thin, approximately 1/100th times of the normal diode. Due to such thin regions of the depletion region, the charge carriers can penetrate the depletion region due to their high kinetic energy. Since the regions are heavily doped, in the sense there will be a very thin layer, as well as the number of charge carriers you are going to find it in the P as well as in the N. I mean the holes in the P region as well as in the electrons in the N region will be more in number. Since they are more in number, their kinetic energy will be obviously higher than that of normal PN junction diode. With a small forward voltage, so with a small, or you can say with a small forward voltage, so since the kinetic energy is high, they can punch through this thin depletion region and they can cross the barrier and reach at the other terminal. This penetration or punching of electrons to the depletion region due to high velocity, or you can say high kinetic energy, this phenomena is known as tunneling, and this happens at very low forward voltage. So because there is a very thin depletion region is there, I cannot expect the tunneling to be happen at 0.7 or 0.8 at a higher voltage. So since the depletion region is very thin, the tunneling effect is observed at very earlier forward voltage. Due to this tunneling effect, the tunnel diode shows a negative resistance region. You can see here. So this is this is the characteristics of tunnel diode. So here current is taken along the y-axis and voltage is taken along the x-axis initially. So as the forward bias is increased, you can see here with a small forward voltage, current is increasing because of the tunneling effect. Since uh, the charge carriers with high kinetic energy, they punch through the depletion region, all of a sudden current is going to increase till a value called as uh, maximum value called as peak value, and this point is known as peak point. The corresponding current is peak current and the corresponding voltage is referred as peak voltage. After this voltage, if you increase the forward bias further, the voltage is increased further. At the same time, the current is going to decrease because of its negative resistance property. Even though voltage is increased beyond the Vp value, but the current is going to decrease. but the current will decrease until a certain point, that is, which is known as valley point. After this valley point, again the device is driven into saturation stage, so where both the current as well as voltage are going to increase. So this is the characteristics of tunnel diode. Next one is the pin diode, that is nothing but p layer, intrinsic layer and n layer diode. So this is the diode obtained by sandwiching a pure intrinsic material I between p type and n type of extrinsic semiconductor is called as pin diode. So here the middle layer is nothing but it is an intrinsic layer. So this layer is made up of an intrinsic material. Intrinsic material in the sense it will be a pure form of semiconductor. There won't be any doping will be done in the middle layer. Only doping will be done, or doping is carried out only at the exterior layers, that is N9 uh, P region. So because of the intrinsic layer, you can see the conductivity of intrinsic layer is intrinsic semiconductor materials is very less. So to have the higher value of conductivity, we do something called as doping, and such doped semiconductor materials were referred as extrinsic semiconductors. Here you can see the p layer and n layer both are extrinsic semiconductors, and the middle layer is an intrinsic layer. So the middle layer offers very high resistance to the flow of electric current since it is not doped. So as I told you, so it is pure form of semiconductor. It is not doped. That's why it will show you a high resistance. We will see its operation whenever it is forward bias. Forward bias in the sense if E is connected to positive terminal and N is connected to negative terminal. So here initially obviously the resistance will be high. So if you go on increasing the forward voltage, obviously, so in a forward bias study we have seen that the holes in the P region, they will try to move towards the N region, and the electrons in the N region, they try to move towards the P regions. Means to say the charge carriers will be moved towards the junction. Means this depletion layer that is formed by the intrinsic region is going to decrease. As this layer is going to decrease, the resistance offered by this semiconductor material is also going to decrease. You can see here the resistance is a variable. This is shown with a variable resistance. So with a small forward voltage, the resistance will be very high. As we increase the potential, forward bias potential, the resistance offered by the intrinsic material is going to decrease. That's why the resistance will try to decrease, will be decreasing. That's why it can be represented with a variable resistance in the forward bias condition. Next, whenever the pin diode is reverse biased in the sense the p layer is connected to negative terminal of the battery and n layer is connected to positive terminal of the battery. In this case, the holes will move away from the junction, as well as the electrons in the n region will also move away from the junction. In the sense, they will try to increase the depletion layer that is formed by the intrinsic semiconductor. But this, so you can see here, this is analogous to a capacitor. This is analogous to a capacitor. You can see the P layer, it acts like a conducting plate, and N layer, it again acts like a conducting plate. These two plates are separated by an insulating medium here. So it looks like a capacitor, that is two plates, they are separated by a dielectric medium. It is analogous to a capacitor. So the capacitance value depends upon the depletion layer width. So if the reverse bias is increased, the depletion region is going to increase for certain amount of time. After that, the depletion layer width will become constant. It doesn't increase further with an increase in the reverse bias voltage, or you can see, or you can say the capacitance value, it becomes constant. This junction capacitance or transition capacitance, it depends on the width of the width of the depletion layer. Since this depletion layer is going to increase initially for certain amount of time, after that it will become constant. It is assumed to be a constant capacitor whenever it is reverse bias. Again I am telling you, whenever it is forward bias, it behaves like an variable resistance, and whenever it is reverse bias, it behaves like a constant capacitor. You can see the characteristics here. So initially the resistance will be very high with a small forward voltage. As the forward voltage is increased, or as the forward current through the diode increases, the resistance is going to decrease. And here you can see the reverse characteristics. So initially whenever the reverse voltage is small, so obviously the initially there will be an increase in the depletion layer is observed, means that capacitance decreases initially. After a particular point of time, the depletion layer width will become constant even though there is a rise in the reverse bias. So that's why it is shown constant here. Okay, so next one is the Schottky diode. It is also referred as hot carrier diode, because hot carrier in the sense the kinetic energy of the charge carriers will be very high here. So as in case of tunneling diode, here also the charge carriers kinetic energy will be very high. So these uh, charge carriers are with a high kinetic energy are referred as hot carriers. Unlike normal diode, it is an metal semiconductor junction diode. So there will be two terminals, and it is unipolar. Means unipolar in the sense the current carriers are only electrons here. So in case of normal diode, the current conduction is due to both holes as well as electrons. They were referred as bipolar. Unlike normal diode, it is an unipolar diode, but there will be two terminals, and here the junction will be found between the metal and semiconductor layers. These diodes are specially manufactured to solve the problem of fast switching action, that is on and off action at higher frequencies. I cannot use the normal diode at higher frequencies because of its uh, because of its slow reverse recovery time. I cannot use them at the higher frequencies. For low frequency applications, normal PN junction diodes are okay. So if you use the normal PN junction diodes in rectifiers, for low frequencies they will be working fine. For higher frequencies, they won't be clipping the certain portion of the signal properly, or for higher frequencies the performance is going to deteriorate. To have the proper performance even at the higher frequencies, instead of normal diodes, the Schottky diodes are used. So here the construction you can see here, this is an metal, this layer is an metal, and this layer is an N type of semiconductor layer. So these two are combined here, and there is a junction made here, and this junction is referred as a metal semiconductor junction. Again I am telling you, this is a metal region and this is an N region. These two are combined, the special fabrication technique. The metal side, an electrode is attached, and this is known as anode, and towards the end region one more electrode is attached, which is known as cathode, and symbolically it is shown like this. It consists of a metal to semiconductor junction. Usually N type of silicon is used as a semiconductor, and metal used may be platinum, tungsten or gold. Here the metal that we are talking about, so which kind of metals are used ಅಂತ ಹೇಳೋದಾದ್ರೆ, it can be made up of gold, or it can be made up of platinum, or it can be made up of tungsten. Here the metal acts as anode, as I told you, metal acts as anode, and N-type silicon it acts as cathode. So obviously in both these layers, the electrons are the majority charge carriers. As I told you, it is an unipolar device in the sense the current conduction here is only due to electrons, which are the majority charge carriers. So working of the Schottky diode, when a contact is made between metal and semiconductor, the electrons from the N side enter into the metal immediately, because the kinetic energy of the electrons in the N region is higher than the kinetic energy of electrons in the metal. Obviously In electrons, oh sorry, one second. So here also the electrons will be there, ಇಲ್ಲಿ ಕೂಡ electrons ಇರ್ತಾವ, and here also the electrons will be there. But the thing is, if you compare their kinetic energy, the kinetic energy of electrons that are in the n region is higher than that of the kinetic energy of electrons that is there in the metal. So whenever the junction is formed, due to the high kinetic energy, the electrons move from cathode region to anode region, or you can say n region to metal region. There is a heavy flow of majority charge carriers from n region to metal. Due to the high kinetic energy, the majority charge carriers from n region are called as hot carriers. So because of their high kinetic energy, the same kinetic energy concept of the charge carriers we have mentioned it in the tunnel diode. So here also the kinetic energy is high. Since the kinetic energy is high, so as soon as the junction is made, electrons will be rushed to in the electrons will be rushed towards the metal region from the n region. So that's why these are referred as hot carriers. Hot carriers. Now if you see the VI characteristics of Schottky diode, you can see the red line, the red characteristics, uh, they look like a normal PN junction diode here only. So ನೀವು ನೋಡಬಹುದು normal PN junction diode characteristics ಹೆಂಗಿರುತ್ತೋ ಹಂಗೆ ಇರುತ್ತೆ. The only difference you are going to find it here is in case of Schottky diode, while discussing about the forward bias characteristics. So this is the forward bias characteristics of a PN junction diode. Let's say the cut-in voltage is somewhere here, but for the Schottky diode, so since it is an hot carrier diode, the forward junction potential is going to reduce. You can observe here, for normal PN junction diode, the cut-in voltage is somewhat here at higher voltage, but for the Schottky diode, it is at the lower voltage. Means to say the forward junction potential is reduced. So for the in case of reverse bias characteristics, you can see here with Schottky diode, I can achieve the breakdown at the earlier stage only. So here you can see for the normal PN junction diode, the breakdown is achieved somewhere here at this point, but for the Schottky diode, the breakcore is achieved at the earlier stage only. And another difference is the reverse leakage current. In case of normal PN junction diode, the reverse leakage current will be very small, but by Schottky diode, you will be getting a large leakage current, or you can say reverse leakage current. These are the differences in their characteristics when you compare with the PN junction diode. One thing is the cut-in voltage is reduced. Another thing is the breakdown is achieved at the earlier stage. And another thing is with Schottky diode, I can have the large reverse recovery current, reverse leakage current. Next we see the applications. They are used in radar system, high-speed TTL logic circuits, EDCs, that is analog to digital converters, in case of SMPS, that is switched mode power supplies, and in high frequency applications such as digital computers. So this one I have already told you, for as the frequency of the supply voltage increases, the normal diodes won't be suitable for the operation because of their slow reverse recovery time. Since with the Schottky diode, I can have the fast reverse recovery time, in the sense I can use them even at the higher frequency applications without any deterioration in their performance. Thank you.